So good evening, everyone. My name is Kachach. I'm from Civil Engineering Department at King Fahd University of Petroleum and Minerals at Saudi Arabia. So today I have the pleasure to share with you my presentation concerning post-fire residual strength and stiffness degradation in FRP-Reinforced concrete structure. So this is actually the outline. We're going to start for sure by introduction. Then after that, we will see the thermal degradation process of FRP and mechanical property degradation. After that, we will move to the post-fire and environmental effect, protective measure, and we will conclude with a conclusion. So before starting, I'd like first of all to start quickly by introducing what does mean FRP. So what makes it special. So FRP is fiber-reinforced polymer, and it combines two key ingredients. The first one is, as you can see, the fibers like glass or carbon for high strength, and the second one is the plastic like polymer or epoxy, etc., to hold everything together. So we can say that the fibers bear the load while the resin hold everything together and protect the fibers from damage. So you can think of it like a teamwork material where the fibers bear the load while polymer try to keep everything together, as I have just mentioned. So now let's move on to the mechanical properties. So, or what makes FRP special? Actually, it has high tensile strength, especially for the carbon FRP compared to the steel, the traditional one. And secondly, it has low elastic modulus. Yes, it is strong, but it is less stiff than the steel. And finally, lightweight. And this is actually one of the most significant advantages of FRP. It has low density compared to the steel. So without forgetting also corrosion resistance. So FRP does not corrode, which improves durability, especially in harsh environments. And it is an anisotropic behavior. It has anisotropic behavior. This means that it has high strength in the same direction of FRP. So this will help engineers put FRP, especially when it is needed. And as we already know, there is no material perfect. So FRP also has its limitation. And first of all, it has low dexterity. This means it is brittle and it can break anytime without previous warning. Also, sensitivity to high temperature, which makes sense. It's actually our problem. And it has high cost, especially for carbon FRP compared to the traditional material like the steel. And finally, environmental sensitivity, like it can be affected by the humidity, UV exposure, etc. So now let's move on to the mechanical property degradation. And now I will explain like how the strength of FRP decreases when exposure to fire. So actually FRP materials are very sensitive to high temperature because like the main problem starts at the glass transition temperature, which called TG, which is between 100 and 118 degrees Celsius. Like at this temperature, the resin inside the FRP begins to soften. So when the resin softens, the bend between the fibers and the matrix, like it becomes weak, which makes sense. So this causes a rapid reduction in tensile strength. And actually, some studies also found that if the temperature rises above 300 degrees Celsius, like the strength drops significantly. And at temperature between 400 and 500 degrees Celsius, FRP can lose between 13% and 18% of its original strength, as Protectio have already mentioned in their studies. And also, it is important to understand that this strength loss is not gradual, like it happens quickly after exceeding TG, and the damage is permanent even after the structure cools down. So FRP reinforcement lose strength rapidly under fire, like which can seriously affect the safety of the structure. So now let's move on to understand like how fire affects stiffness and elastic modulus in FRP reinforcement concrete. So actually stiffness is very important because it controls how much a structure bends or deflects in the load. Like, because actually you already know that the elastic modulus represent the rigidity of the material, right? So when the temperature increase and reach the glass transition temperature, which is between 100 and 118 degrees Celsius, the resin inside the FRP starts to soften. So when this happens, like the material becomes less rigid. So as a result, the elastic modulus decreases and the structure becomes more flexible. So if the temperature is above 300 degrees Celsius, the reduction becomes much more serious. So research shows that stiffness can decrease by more than 15%, as Safi have already mentioned in their studies. So at temperature above 400 degrees Celsius, stiffness can also completely collapse, which is very dangerous. So it is also important to understand that this reduction happens quickly after exceeding TG, which we mentioned in the introduction, and it is not fully recovered after cooling. So because of this stiffness loss, the structures may experience larger deflection, maybe reduce this. For sure, it will reduce the stability and high risk of failure to collapse. So we can conclude, based on this slide, that the fire exposure significantly reduced stiffness and rigidity of FRP reinforcement members, making them more vulnerable to deformation and instability. For the band strand and degradation, actually, which is one of the most critical problems under fire exposure, because in FRP reinforcement concrete, the band between FRP bars and the surrounding concrete is essential. Why? Because this band allows the reinforcement and the concrete to work together as one composite system. So, however, when the temperature increase and reach the glass transition temperature, which we mentioned TG, the resin inside the FRP begins to soften. So once the resin softens, the bond between the FRP and the concrete weakens significantly. So the adhesion reduces and the load transfer between the materials becomes less effective. Research also showed that at temperature around 115 degrees Celsius, the residual band strength can drop to about 17% of its original value. And in some cases also, the band strength can decrease by up to 19% when the temperature exceeds TG, as Ahmed and Qadr have shown in their studies. So very often, the band failure it happens before complete material failure. That means that the structure may fail because the reinforcement and concrete stop working together. So even if the fibers are not completely discharged, which makes sense. I think that's all. And now for the post-fire and environmental effects. So now we will talk about what happens after the fire is over. And actually, this is the core of our presentation. So even when the fire stops and the structure cools down, the damage remains. So the FRP bars do not recover their original strength. After fire exposure, the tensile strength becomes much lower and the stiffness is also reduced. So this means that the structure cannot carry the same load as before. And in some fire tests, also beams lost up to 70% of their load capacity after just 2 hours of fire. So even though they did not collapse during the fairing. So I hope you get the point. So another important problem also is the band between FRP and concrete. For example, after fire, this band becomes weak, as we have just mentioned in the previous slide. So even though they did not collapse during the fire, but it will not work. So sometimes the structure may look fine from the outside, but inside the reinforcement has already been seriously damaged. So even if the structure survives the fire, its residual strength itself and safety level may be greatly reduced. For now, I will discuss the compressive behavior and confinement of FRP reinforcement concrete, and always under fire exposure. Actually, FRP is often used to confine concrete column. This confinement increases compressive strength and improves ductility under normal temperature. However, under fire exposure, this benefit is significantly reduced. So when the temperature rises and exceeds the glass transition temperature, the resin inside the FRP softens. So as a result, these confinement effects become weaker. This leads to a reduction in compressive strength and elastic modulus of the concrete. And also the concrete can no longer resist axial loads as effectively as before, because fire exposure increased slippage between FRP and concrete. So we can say that instead of improving performance, the FRP confinement loses its effectiveness at high temperature. So fire exposure significantly reduced the compressive capacity and confinement efficiency of FRP reinforcement concrete, leading to lower strength, lower ductility, and higher risk of brittle failure. So now I will we will move to protective measures, starting with concrete cover, some kind of improvement or some kind of solution. Actually, one of the main ways to protect FRP reinforcement from fire like it's by increasing the concrete cover. I mean, the concrete acts as a thermal barrier, right, between the fire and FRP bars. So when the concrete cover is thicker, like it slows down the heat transfer to the reinforcement, and this will delay the temperature rise in the FRP bars and postpone reaching the critical glass temperature. Research also shows that increasing the concrete cover can really significantly improve the fire resistance time. For example, a concrete cover of about just 17 millimeter can allow a beam to resist fire up to 19 minutes, which is very important. However, it is also important to understand that the concrete cover does not completely prevent damage. Like it only delays the heating process. So if the fire lasts long enough, the temperature will still reach the FRP reinforcement and degradation will occur. So increasing, like the most important point you should get that increasing concrete cover is an effective and simple protective measure. Like it improves fire under time, but it cannot fully stop strength and stiffness degradation during prolonged fire exposure. We have also another solution. So about insulation system, it's also as a protective measure against fire. Like in addition to increasing concrete cover, external insulation matches can be used to protect FRP reinforcement members from high temperatures. So let me explain more. This insulation system acts as an additional thermal barrier, like they reduce the rate of heat transfer from the fire to the structural elements. So common type of insulation include, as you can see in the screen, ceramic fiber blankets, calcium silicate board, etc. Actually, there are many. So when exposed to fire, some of this material expand or create a protective layer that slow down the heat penetration. So researchers prove that insulation FRP strength beams perform much better during fire exposure. Like in some cases, being protected with insulation experience only about 20% loss in flexural strength after 2 hours of fire. So this is a significant improvement compared to unprotected members. However, it is also important to understand that insulation systems delay the temperature rise, like the concrete cover, but they do not completely eliminate thermal damage. If the fire lasts long enough, degradation of the FRP will still occur. So now let's discuss about the hybrid reinforcement system as another protective strategy against fire. Actually, hybrid system combine FRP reinforcement with traditional steel reinforcement in the same section member. I mean, the idea behind this approach is to benefit from both material, I mean the steel and the FRP. FRP provide corrosion resistance and high tensile strength, while the steel offer better performance at high temperature. So during the fire exposure, like the steel reinforcement can maintain its strength longer than FRP. This helps the structure continue carrying the loads even when the FRP becomes to degrade. So this we will have like some kind of improvement. Researchers also show that hybrid beams generally perform better in fire conditions compared to beams reinforcement only with FRP. They have improved also the fire resistance times and better residual capacity after cooling. So, however, it is also important to note that strength and stiffness degradation still occur. If the fire duration is long or the load level is high, the structural performance will still decrease significantly. So you can get, like, the final point is that hybrid reinforcement systems improve fire performance compared to pure FRP systems, but they do not completely eliminate the problem of thermal degradation. So now let's move on to the gaps. Actually, even though many studies have been done on FRP under fire, but based on my research, I found that there are still some important gaps. First, we still do not have accurate models to predict the long-term strength of FRP structure after a fire. Like most research focus only on short-term results. Secondly, is that the reason used in FRP is very sensitive to heat. So we need to develop better fire resistance resin material. The third point is that insulation systems helps, but they are not perfect. So more effective and affordable fire protection methods are still needed. And also, finally, engineers need to clean guidelines to assess FRP structure after a fire and decide whether they can be repaired or must be replaced. There are two choices. One of them must be decided. So future research should focus on improving materials, protection system, and post-fire evaluation method. So to conclude, FRP reinforcement, just to give you an overview about what we have just discussed. So FRP reinforcement offers many advantages under normal conditions such as high strength, low weight, and excellent resistance to corrosion, etc. So however, its performance under fire exposure is a major concern. So when the temperature reaches the glass transition temperature, the resin begins to soften. So this leads to a rapid reduction in tensile strength, stiffness, and bend capacity, etc., which we have just explained. So protective measures such as increasing concrete cover, using insulation system, applying hybrid reinforcement can improve fire resistance. But however, this solution only delay the damage; they do not completely prevent it. So therefore, when using FRP reinforcement in structure where fire risk exists, so I prefer proper fire protection design at post-fire system are essential. So in summary, like we can say that while FRP is an excellent material under normal condition, its vulnerability to high temperature must be carefully considered in the future structure design. So these are the references, and thank you for your attention. Please, if you have any questions, feel free to ask.